lecture we'll start talking about the data link layer. So we've talked about physical layer, where we say that we get data bits from the DLL and we send out signals. And above the data link layer is the network layer, the transport layer, and the application layer. So here essentially the symbol, I should say the unit that we were considering was called the symbol. So symbol is a signal which represents one or more bits which are sent from the higher layer. At the data link layer, we try to make sense of these bits. Okay, so let's say that symbols are coming in, and the physical layer converts it to bits and sends it to the data link layer. We try to make some sense of those bits which are coming in. So let's say we are getting 1 0 1 0 0 1 whatever, right? These are the bits coming in from the physical layer. What do they really mean? So we need to make sense of it. And of course the ultimate meaning of those bits is going to be understood by the application layer. But what we want to at least say over here at the data link layer is which bits together mean something together. Okay, so suppose you have these bits over here, and these are coming in, they make no sense at all. So at least we have to say that maybe the data that was coming in began here and ended somewhere else in this bit stream. And the term to use there for that data unit is a frame. So this is the term used at the link layer. So we talk about frames. At the data link layer. And at the network layer we talk about packets, which is just one unit of one data unit. And one data unit at the transport layer, at TCP at least. So TCP talks about segments. Okay, so effectively each of these is just a set of bits which make sense at that particular layer. So here we are looking at the smallest data unit, which is just one symbol, or the bits represented by this symbol. But then we have to make more and more sense of them together. So maybe there are several bits sent by a particular entity over here, and we are going to group those all into a frame. Okay, and maybe a frame has a set of headers that we need to look into. Okay, and similarly at the IP layer, we look at an IP packet, which is a group of bits which start with an IP header, and then there's some data fields and so on. Okay, so what do we need to know about a frame? So first of all, a frame starts somewhere. So we have these bits coming in. So we need to say that the frame coming from somebody else starts, and where this actually ends. And once we have that information, we can look at the various parts of this frame. So there may be some sort of a header over here of some kind. depending on the particular link layer protocol we are dealing with. Okay, so we look at the example given in your textbook, and it starts off with something called HDLC. And that stands for High Level Data Link Control. And this is used as a layer 2 technology in wide area networks. So layer 2, that is the data link layer in wide area networks or WANs. So if you think of the internet, you would, at the edges you would have LANs, local area networks, which are small networks. But then you go to larger networks which have wider geographical coverage, and those would be called WANs. So it's just a classification, and WAN covers a larger geographical area, and it may have many more routers and switches than a local area network. So in a WAN you may have two routers connected to each other, and these will be sending some information to each other using some particular physical layer, using some particular line coding. But on top of that we need to have a data link layer, and you could use something like HDLC. But there are other protocols also which these WANs use. So what do we have? What does the frame look like? So the frame it has a begin sequence, followed by a header, followed by a body, and of course it ends with an end sequence. But how do you know that the bits that you got were correct? Because there may be some bit error due to any particular reason. It may be noise or interference from a neighbor or something like that might have caused a bit error. So the HDLC frame also has a CRC there, which is essentially some extra bits that you put in, which will help you verify that there are no errors in this particular frame that was sent. Okay, but there are some limitations. So you can't detect, in fact, all possible errors with a CRC, but you might be able to detect certain errors which may be good enough for practical applications. Okay. So the begin sequence is 8 bits long. So you have a bit string coming in, and you need to know when this frame is beginning. So this particular sequence of bits will tell you when the frame is beginning. And the header is 16 bits. This body is of variable length. The CRC has, I think it has 16 bits. And the end sequence is actually 8 bits. So I don't have this number in my notes, but I'll let you know. I think it's either 16 or 32-bit CRC. Okay. I'll just put a question mark here. Okay. So you have a sequence of bits coming in, and let's say you want to know when a particular frame is going to start. So the begin sequence and end sequence are the same. And it's essentially this sequence. Several ones, 6 ones with zeros on either side. So what happens on this HDLC link between, let's say, two routers is that you continuously send this sequence. So I'm just going to call this sequence for short. So what you do is you send sequence one after the other. If there is nothing to send, no data to send, you just keep sending this continuously. And once, of course, there is some data to send, the frame begins. Okay, and finally we have the end sequence, which in our case is just the sequence, so I'll just write that over here. So you have CRC followed by the sequence again. Okay. So the HDLC protocol is running at both these ends, and as long as there is just sequence coming in, it just ignores it. It doesn't have to worry about anything. No information is coming across. And this sequence just helps in clock synchronization and things like that, because we are always switching once in a while from 0 to 1. Okay, so we can do clock synchronization. So this helps in clock synchronization. Now, let's say you suddenly get a header, and you get a sequence followed by some other, let's say a header over here. Okay. So, and then there is some data. Okay, and let's say we are able to recognize this change from here to here. And then we know that the frame has begun, and we got the CRC. The CRC is going to be used to ensure that there are no bit errors ideally, and of course there may be some rare bit errors which manage to get through. Then again we switch back to the sequences. So here we have the body. Okay, so it's just that as long as we have these sequences, we don't worry at all. We don't have to figure out what bits are being sent and maybe send it up to the higher layer and so on. But once we get the header, we have to figure out what the header is, the body, the CRC and so on, and then we may have to send information to the higher layers. So obviously the question that comes to your mind is, what if the sequence appears somewhere over here? What if the sequence appears in the body? Then I might think that the end sequence has come and that's the end of the frame, and that's going to be a problem. Or what if the header itself begins with this sequence? Then there's going to be confusion. I mean, is the first set of bits here a sequence, or should I consider it to be the header? I mean, the link layer may get confused. So obviously I want to ensure that this bit sequence doesn't appear anywhere over here. And how is that possible? I mean, because obviously you may have a text file or something you're sending in the body where these bits in fact do occur. I mean, what is so unusual about this? Why shouldn't it occur in some file that you're sending across? Okay. So clearly it might exist in the body and so on. But in that case, the link layer at the sender has to actually change it in some way so that it doesn't cause confusion. And that is done by something called bit stuffing. So what are we going to do? So suppose in the body, what we have is, let's say this is the body at, let's say the okay, this is the set of bits that you want to send. Let's say it's something like this, and somewhere you have this particular bit string which appears. So we have to change this at the sender itself. And what we are going to do is we will have to insert some bit somewhere in order to change this. So to ensure that sequence does not occur. So the HDLC at the sender is going to change this, it's going to insert bits to change this sequence. But then at the other end, before we actually analyze what the body is, we will have to remove those bits and then analyze the body. Okay, because the body may be, let's say, a file or something like that. So you want to remove these bits which were inserted by the HDLC at layer 2. And only then deal with them. For example, handing it over to the higher layer and so. So how are we going to do this bit stuffing? Now let's look at the algorithm in HDFC. So here what we do, if within the frame, in any of the fields, now starting from the header and so on, if you see 5 consecutive ones, then insert a 0 after that. So this is, so let's take an example. So suppose these are the actual bits of the body. Before the bit stuffing. So suppose you had somewhere 0 and then let's say 5 ones, let's say followed by a 0. And let's say here we had 6 ones followed by a 0, and somewhere let's say we had 7 ones followed by a 0 and so. So this is the bit string that we want to send across. Okay, so what we are going to do according to this algorithm, if we see 5 consecutive ones, then we insert a 0 after it. Okay, so let's think about it. So we are going here, we count 1, 2, 3, 4, 5. So we put in an extra 0. Okay. over here. Now we go on 1, 2, 3, 4, 5. So we're going to insert a 0 over here. 1, 2, 3, 4, 5. So we insert a 0 over here. Okay. Here there are only 2 ones, so there's no need to insert anything. Okay. So this is a simple enough algorithm. The sender just has to see where it's getting these bits. Okay, what are the bits coming in, and if at all there's a set of consecutive ones, okay, 5 ones coming one after the other, you add a 0 after that. Now what is the receiver going to do? So the receiver has to remove these bits. Okay. So the receiver knows that this algorithm has been used at the sender. So this I should just say that this is at the sender. Okay, at the sender. Now at the receiver, what do we do? So these are the bits coming in, and notice that we've also stuffed some bits over here. So just to complete this, I'll just write this over here, 0, 1, 2, 3, 4, 5, and then I have this 1, 2, 3, 4, 5, and then so these are the bits coming to the receiver, or these are, I should say, these are the bits transmitted. Now the receiver has to remove these bits before it tries to make sense of the bits. So how do we do that? You might think over here. So there are 5 ones over here. So what should I do after that? I mean, is it possible that we have 6 ones continuously coming in? So the answer is no. You're never going to have 6 ones coming continuously in the body, right? Or anything after the initial header sequence, right? So you have the starting sequence, which is that particular sequence of 1 followed by 6 zeros and then a 0. I beg your pardon, 0 followed by 6 ones and a 0, and then at the end too you have the same bit string, but in between you shouldn't have that. Okay, so because of this bit stuffing, you will never have 6 ones coming continuously. Okay. And wherever you have 5 ones, there is always an extra bit 0 put in there. Okay, so notice here you didn't have 6 ones. Okay, so it's not that wherever we have the sequence bit string we modify that. That's not what we are doing. If at all you see 5 consecutive ones, I put a 0 in over there. Okay. Whether or not I did have that full sequence or not over there, the full sequence bits. Okay, so what I'm going to do is wherever I see 5 consecutive ones, I remove the 0 which comes after that. So first let's look at the simple algorithm assuming no bit error. So if 5 ones occur, then they must be followed by a extra 0 which was stuffed. So then we remove the stuffed bit which is 0 following them. Okay. So just to summarize, so what we are doing at the sender is you have your sequences which you're sending out, and then once you have an actual frame to send, you look at the bits. If at all you have a string of 5 ones, you insert zeros after those 5 ones, and then you send that out. Now at the receiver, we are sure that once the frame starts, you'll never see that sequence of bits corresponding to the initial start or end sequence, okay, because of this bit stuffing. Okay, so you know that a frame has begun over here. Okay. And so you start looking at those bits, and if you see 5 ones, you know that there has been a bit stuff of 0 following it, then you remove it. Okay. So now we have to look a little bit more carefully. Okay. So this is sort of at a high level what we are doing. Okay. But we have to look at other cases. What if a bit error occurs? Okay. Or what if you have an end sequence? If suppose you're seeing all this is fine, but at the end you actually had an end sequence. So there you didn't do any bit stuffing. So let's say we took that as an example. So we had, let's say this was the end sequence. And here there is no bit stuffing because it doesn't correspond to the interior of the frame. Okay. So here, of course, we are going to use this algorithm. We are going to remove this 0. We are going to remove this. That's fine. But then here we have 5 ones, and then what do? Then it's followed by a 1, and so that's when we say that the end sequence has been received by the other end. Okay. So here's a little bit more detail. So at the receiver, suppose we have 5 ones. Okay, so of course you have to have let's say that there was a 0 here. So 5 ones. If there is a 0, so let's look at it here. If this is followed by a 0, then what we do is we assume that it was due to bit stuffing and remove. So what if it is a 1? Then what do we do? I mean, do we assume that it is the end sequence? It's probably going to be the end sequence, so we don't do anything. So we wait for the next bit. So these are the next 2 bits. Then we assume that it was the end sequence, which told us that the frame ended. Okay. But what if we got 1 1? Now this would not occur in the, if there was no bit error, because if it was within the frame, then I should have seen a 0. I should not have seen a 1. And if it was an end sequence, then I should have seen 1 0, not 1 1. So what do we do here? So in this case, we assume that an error has occurred. Okay. And what we do is, we discard the entire frame. Because you can't do much better than that. If there's a bit error somewhere, there's no point in dealing with that bit string at all. So what do we do if we have got an error? We are a little bit confused. We didn't get an end sequence, and this should not even be there in the body of the frame. So what should we do now? I mean, maybe we are in the middle of the frame and there was a bit error. What if this bit got flipped to a 1? We would see something like this. We would see a string of 7 ones. Okay. So suppose this one came in error, you would actually see something like this. And then maybe we don't see the sequence again because we are in the middle of the frame still. Okay. So what we do is we wait till we see sequence again. Okay. So we discard the entire frame, and in fact we discard everything until we start seeing the sequence again. Okay, and then we are sort of back in business. Maybe we have lost a particular frame, but now we are at least getting the sequences regularly. And again, if we suddenly see something other than a sequence, we assume that the frame has begun. Okay. So can this check for all possible errors? Not really. I mean, let's say one of these bits flipped to 1. This is not going to take care of that. So we need an additional mechanism to check for bit errors. Okay. So that we'll look at next when we discuss the CRC. Okay, so CRC stands for cyclic redundancy check. And the CRC are extra bits put into the frame which are going to help us figure out if there was some bit error somewhere in the frame. So what exactly does the CRC do for us? So let's go back a little bit to the frame for HDLC. So we said it begins with a sequence, which we saw what that particular sequence was, and it ended with the same sequence. But inside there was a header, a body, and the CRC. So the CRC's task, or the job of the CRC, is to help us detect if there was an error anywhere within any of these bits. So essentially the CRC does a sort of coding for us. So we start with a data word. And let's say that's n bits. So in our case, of course, the data word would be the header and the body. But in general, if you're using CRC on any data, you just take the entire data of n bits and then you append to it a CRC which consists of some k bits. Okay. So this is very much part of coding theory. So this is the data word, and the entire thing put together is called the code word. So how does the code word help us detect if there are any bit errors? Okay, so let's think about the space of data words. So this is an abstract vector space. Just think of all 2 to the power of n words of size n bits. Okay, so these are all n bit words all possible combinations of n bits. So there are 2 to the power of n of these. So these are all possible data words. But what we are transmitting is n plus k bits. So what is the space of code words? So here we have a much larger space. I'm just drawing it in this fashion. So there are 2 to the power of n plus k of these. Okay. This many possible combinations of n plus k bits are possible, but not all of them are valid code words. So the way we construct this CRC is such that only some of these are valid code words. So maybe this one is a valid code word, this one is a valid code word, and so on. And the number of code words are equal to the number of data words. So only 2 to the power of n out of these possible, I should say, space of possible code words, or I think to be clear, maybe I shouldn't say space of code words. I'll just say space of let's say space of n plus k bit words, let's just say. Okay, so out of that only 2 to the power of n are valid code words. So for every data word over here, I have a particular data word. It has a unique CRC. So one of these will correspond to one of these code words. Okay, so each of these gets mapped over here. Okay, so how does this really help? Well, because we are transmitting only one of these code words. So suppose we receive n plus k bits which do not correspond to a code word. Then that essentially tells us that there was a bit error. Okay, so suppose I transmitted this one and let's say 1 bit was an error. Maybe so suppose I transmitted this particular code word, and instead of that there was a bit error, because of which I got this other word of n plus k bits. Now clearly this is not a valid code word. This one over here is not a valid code word. So that means there was something wrong. There was probably a bit error. Okay. So you might wonder, but what if the bit errors make us go from one code word to another one? Okay, one valid code word gets switched to another valid code word because there were too many bit errors. Then we are in trouble because we wouldn't know that there is a bit error because this is a valid code word. Okay? So we have to design this so that these are far enough apart. And to decide what is far and what is close, we use something called Hamming distance. So what is the Hamming distance between two code words? Well, it's the number of bits which are different in those code words. So it's the number of bits which are different in the two code words. Okay. So suppose I have a code word, let's say it's something like this. And there's another code word. So most of the bits are the same except for a couple of bits over here. So the Hamming distance is 2. Okay. So suppose this code word was transmitted and both these bits were received in error, we might actually get this code word. So how do we say what is the quality of a particular coding scheme? Okay, so we want all of these code words to be fairly far apart from each other. We want the Hamming distance between pairs of code words to be large, so that you need lots and lots of errors to go from one code word to another. So for that we talk about the Hamming distance of the code. So this is Hamming distance between two code words, and there is also the Hamming distance of a code. So it's the minimum Hamming distance over all pairs of code words. And if this minimum Hamming distance is large, then you are in business. That means you need lots of errors to go from one code word to another. Okay, so in this case, for example, if there was a single bit in error, you could never go from this code word to the other. Okay. So in general, whenever we design codes, we want the Hamming distance to be large. So let's talk about how to generate CRCs, and for that we need something called a Galois field. And the one we are going to deal with is GF2. So this is a finite field with two elements. And the two elements, as you can guess, are 0 and 1. Now this finite field has addition and multiplication defined on it. And addition is just an XOR. So I'll just write it as plus. So 0 plus 0 is 0, 0 plus 1 is essentially X. We are XORing the bits. Right? 0 plus 1 is 1. 1 XORed with 1 is 0. Okay. And multiplication is defined in this way. This is just the usual multiplication. So 0 multiplied by 1 is 0, except 1 multiplied by 1 is 1. So everything, all others are 0 because we are multiplying by 0 in either one of the elements. So CRC comes under a topic, it's a type of cyclic code. And or I should say it's based on a cyclic code. So the entire code word would be belong to a cyclic code. Okay, CRC is just the last few bits. So we said that let me just show. So this entire thing is the code word, and the CRC is created from the data word and it's put at the end over here. But this entire code word comes from a cyclic code, which means that if we have a particular code word, let's say A0, A1 and so on up to AN, these are the various bits. And this is a code word. Then cyclic shifts of this code word are also code words. Then so one cyclic shift is you take this bit here to the front. And this is also a code word. So let's see how we can generate a CRC. So given a particular data word, we need to generate its CRC. So this has something called a divisor or a generator. And the length of this is k plus 1 bits. Okay, so let's take for example, let's say that k is equal to 3. So one particular generator that we may want to use is the bit string 1101. So this is 4 bits long. So let's see how we are going to do it. So suppose the data word is 6 bits long. And one example, let's say that the data is 110110. So what we are going to do over here is essentially long division, just like we were taught in school. Except when we do things like addition, we are going to use these tables. Multiplication and addition, we are going to use these tables. And in the GF2, subtraction is the same as addition. So let's just do long division, and it will turn out that the remainder is going to be the CRC. Okay, so what we are going to do is we take the data word 110, 110, and we append to it 3 zeros. Okay, so this is k bits. And we are going to divide this by the divisor, which is sometimes called the generator. Okay, so we are going to divide. So let's say, so first of all we have to multiply by 1, because the first bit is 1. Now we are subtracting, and it's going to be the same as addition. So what do we end up with over here? Okay, so I'll just write it as plus here like this. We XOR these. Okay, so this one, of course, the first bit is going to vanish off. So we have 0, 0, 0 over here. Okay. And we consider the next bit. Now this first bit is 0, so we have to multiply by 0. Then we end up with 0 over here. Right? 0 multiplied by this entire divisor. We XOR, right? And we're left with 0, 0, 1, and then we take the next bit, 0. So again we multiply by 0. Okay, so we are multiplying this divisor by 0, and we are XORing. So 0, 1, 0, and we're bringing down the next bit. Again we are left with zeros. And now it's getting a little bit interesting. We have a bit 1 over here. Okay, so I multiply by 1. And XOR individual bits again. So I'm left with 1, 0, 1. Okay. And now we have the last bit. So again I have 1 in the leading bit over here. So I have to multiply by 1. So we are left with 1, 1, 0, 1. Multiply by 1, and we XOR bits together, and we are left with 1, 1, 1. So this is the remainder, and this is in fact the CRC. Okay. So what is the code word going to be? The code word is going to be the data plus the CRC appended. So 110, 110 followed by the CRC. So given a particular generator, we can divide this way and get the CRC. Okay. So before we go into a little bit of theory about how to choose a good generator and so on, where we'll talk about using certain polynomial notation, polynomial arithmetic to do all of this. Let's talk about how we would actually build a circuit to calculate the CRC first. Okay, so this is for us to see how we are dividing, but we want a circuit, preferably very simple, in order to give us the CRC very quickly. So let's think about how to do this, and let's do it this way. So what I'm going to do is I'm going to take the code word, actually not the code word since I'm trying to calculate, but give the data word. I give the data word followed by the zeros. So I mean what I have over here, okay, the entire data word followed by the zeros. This I am going to feed into the circuit, which consists of shift registers. So you might be familiar with shift registers from some other course, but essentially what we are going to do is every clock cycle we are going to shift the bits this way towards the right. So this is a register which stores a bit, okay, and these correspond to XORs. So each of these stores one bit. And these are shifted to the right by one every clock cycle. Okay, so it's a computer system, right? It's a circuit is being driven by this clock. Every clock cycle we take in one bit, starting with the leading bit, push it here, and then shift it to the right. Okay? And what we are going to do here is that we are going to XOR here with 0, and here we are going to XOR with whatever bit comes over here. Okay. And similarly, whatever is the leading bit over here, we are XORing over here. Okay. So this is going to implement this division for us. So we'll just look at it in a moment. And just to give you some intuition about what we are trying to do, why the circuit makes sense. So just look at this a little bit. So if the leading bit is a 1, let's focus here, then what I'm going to do is I'm going to XOR the next 3 bits with 101. Okay. And if the leading bit is a 0, then I'm going to XOR with 0, 0, 0. Okay. So just look at this example. The leading bit is 0, so I'm going to XOR the next 3 bits, okay, that are remaining, okay, after this step. I'm going to XOR with 0, 0, 0. Okay, so what I'm going to do is I'm going to accumulate in those registers, I'm going to accumulate these numbers. So what you should see is initially of course there's going to be 101, but then I XOR with 101 and then these should be remaining. Okay, so So what I should see in that circuit are these bits. Okay, and finally, so I want to see all these bits, and finally I want to see the CRC too. Okay, so I want these bits to show up, and essentially what I'm going to do is whatever is there in the shift register, I want to XOR either with 101 or with 000 based on whatever is the leading bit currently there. If 0 was the previous leading bit, then I want to XOR with 000, okay, the next 3 bits. But if the leading bit is a 1, then I want to XOR with 101. So let's see if that's going to happen. So initially what's going to happen? Initially, let's say that we have this particular data and code word going through. So we have 110, 110, and we are feeding in 000. So these are the bits which are getting fed in. Okay. I just take the data word, add 3 zeros because k is equal to 3, and I feed it into this circuit, and the bits get pushed one by one to the right. Okay. And initially, let's say that there is a 0 over here. Okay, let's say that we have zeros everywhere. So what's going to happen? Initially I have 1, okay, and of course I XOR with 0, then I get the 1 over here, okay, and so on, and then this is still 0, okay, maybe let me write it there, initialize with 0, so I have zeros here initially, so these get shifted to the right effectively, and let's look at the case when these first 3 bits actually reach all the locations over here. Okay, so 110 comes in over here. Now this is the leading bit is a 1 over here. So we've reached this particular stage now. All the bits have gone into that shift register. We've reached here, 110 have entered. So this is the leading bit. So we've reached this stage where 110 is in the shift register and 1 is the leading bit. So what we are going to do is we are going to get yet another bit into the shift register. So we will have 101, we'll have these 3 bits, 101, and because we had 1 as the previous leading bit, we will want to XOR with 101. Now let's see if that happens. Okay, so this is here, so this 1 goes over here, just look at it this way, in the first case. Right? So we are XORing with 1, 0 and 1. Okay, so we are initially XORing with 1, so we are XORing, this 1 goes here and here, but here we of course we are not taking the leading bit, we are always XORing with 0. Okay, because the choice is XORing with 101 or 000, and the second bit is always 0, so we are always XORing it with 0. Okay, so what do? We have 101 coming in. So initially we have this as the leading bit, and then we have 101. Okay, so we have this bit coming in over here. Okay. So what do we end up with? So 1 XORed with 1, so we end up with 0. So 0 is stored over here now. Here we have 0 XORed with 0, 0. Here we have 1 XORed with 1, which means we end up with 0. Okay, so what are the bits that we have here now? It's 0, 0, 0, and of course this is no longer here because we've already gone through one clock cycle, and the next one comes here. Okay, this particular bit comes here. Okay, so what do we have here? It's 0, 0, 0, 1, and let's see if that's what we are doing over here. Here indeed we have 0, 0, 0, 1, and now because the leading bit is 0, we want to XOR with all zeros. And that's what we are going to do over here. Since the leading bit is 0, okay, we are going to XOR with zeros over here. And essentially what we are going to end up doing with this circuit is we are going to perform exactly these XOR. So we keep pushing in one bit at a time, okay, and depending on what the leading bit is, we either XOR with 101 or 000. Okay. And finally, at the end of all of this, we are going to have the CRC over here. Okay, so we'll end up with the CRC, which is going to be 1, 1, 1. Okay. So the last bits in the circuit will be the CRC. Okay. So once the last bit has gone in over here, which corresponds to this last division, these three bits will be left in the shift register, and you can verify them. Okay. So this is how you would implement calculation of a CRC using this simple shift register circuit. Okay. So what we are doing effectively is that we are taking the last three bits of this particular divisor, okay, which in this case is 101. So effectively we have to XOR either with 101 or with all zeros. Okay, so let me just write that down. So take last k bits of the divisor and ensure that if leading bit is 1, so this leading bit in the shift register is 1, then XOR with those k bits, otherwise XOR with all zeros. Okay, so 000, which has k bits. So at the generator, at the source, you generate the CRC this way. You just send your data word and finally you end up with the CRC. What do you do at the receiver? So let's think about that. So at the receiver we have a code word coming. Okay. And think about it, how are we going to do it at the receiver, right? So you could just take the first bits which correspond to the data word, add zeros and send it through. Okay, and just make sure that the leftover CRC is the same as the CRC that you received. Okay. Or you can just send the entire code word through and you should end up with 0. So let me summarize. At the receiver, you can do one of two things. Let's say option 1. So suppose you get a particular code word of n plus k bits. So this is the data word and the CRC. What I can do is I can take this data word and add k zeros, feed it through the CRC circuit, okay, and check whether the CRC you get matches with this. So whether it matches the received CRC. And if it does match, then we are in business. You assume that there was no bit error. But if there is a mismatch, then there probably was a bit error. So some action would have to be taken. The other option is to feed the entire code word into the CRC circuit. So you feed the entire code word. So let me just redraw that. So in this particular case, we have the shift register. So we wanted to XOR with 101 or 000. So it turns out XORing with 0 is doing nothing. So we could as well get rid of this. Okay, and draw it this way. So we feed in this entire code word in, and if we end up with 000, then we know that the CRC matches the data. So if we end with 000, then CRC matches the data word. Okay, so implementation of CRC is quite easy using these circuits, and we want it to be fast because data is coming in really fast, so we need to be able to check the CRC also very quickly. Okay, so this is one reason why we would use something like CRC, because it's just easy to compute and easy to verify. Okay, so in the next lecture we will talk about a little bit about the mathematics of CRC.